Thank you very much for joining us this evening. We're all looking forward to this talk about the technology and testing of the James Webb Space Telescope. My name is Jennifer Dye. I'm a librarian at the Detroit Public Library. DPL has offered astronomy programs for the last several years. When things fell apart in spring 2020, programs were put on hold for a while. We finally launched astronomy programs on Zoom earlier this year. We feel that these have worked well, and we've just welcomed someone from Norway, so that's an advantage to this. Over the summer, Megan McCullen, director of the Wayne State Planetarium, and I applied to an initiative sponsored by the NASA Goddard Space Flight Center for programming around the launch of the James Webb Space Telescope, which is scheduled for December 18th. Tonight's program is the first, and it's about the technology and testing of the telescope. On December 7th, Dr. Edward Cackett will talk about the science of the telescope. I'd like to ask Megan McCullen to speak briefly before I introduce tonight's speaker, Mark Christensen.
Thanks, Jennifer, and hello, everybody. Some of you are familiar to me and others are new, so thanks for being here. And Jennifer, I was really excited to collaborate with you on this. We're near neighbors and we always talk about doing things together, so I'm glad that we've pulled this together. Yes, for those of you who are unaware of the planetarium at Wayne State, we're located just down the road from the main branch of the Detroit Public Library, and we're actually in a building called Old Main, which I call the Hogwarts of our campus. It's the original high school from Detroit and is now part of the university. And we're not noticeable from the outside because we're an expansion they put in the courtyard. So we're well hidden. We're currently not open to the public because of the pandemic and health risk concerns, but we are hoping in early 2022 to be back on board. And we have a brand new projector and lots of programming we're excited to share with everyone. So I will make sure to get that information to Jennifer when we're able to start hosting our free shows again, so that you all know and you can come join us. And the one other event I wanted to highlight really quickly, which I'll also send to Jennifer to send out to everyone, besides our lecture series we're doing together, we've been doing a sort of travel log series throughout the pandemic as well online, which is mostly called Journeys with Jerry, but Dr. Christensen has also given some for us. And hopefully we'll do another one for us again with some of his work. Our next one of those will be coming up on November 17th at 7 p.m. Where retired Professor Jerry Dunifer will be taking us to large and historic telescopes and observatories of the United States that he has visited. So these are fun, more general travel stories with photos of where he's been, how you get there, what you can see. So they're a lot of fun, and I hope you'll join us for that as well. And now I'm going to stop talking so Jennifer can introduce the person you all came to hear talk.
Okay. I will mention that I don't tend to harvest email addresses from people who register.
Got it. Okay.
If you are interested, I forgot to put my USB drive in. If you're interested, you can send me an email and I will add you to the distribution list. It's fairly simple. It's jdye@detroitpubliclibrary.org. And I will be ready in a few minutes with the USB drive to put that up. But Dr. Mark Christensen was born in Detroit. He had spent his early childhood in Inkster and his teens and college years in Livonia. He is a graduate of Wayne State and Purdue universities. His training was in mathematics and physics. When he completed his doctorate, he joined the staff of the School of Mathematics at the Georgia Institute of Technology, where he worked until 1984. He joined the technical staff of the Defense Systems Division of the Northrop Grumman Corporation, the Northrop Corporation it was at that point, in Rolling Meadows, Illinois, working first as the technical advisor in the area of real-time algorithms for avionics systems. When he retired from Northrop Grumman in 1999, he was the vice president of engineering for the Rolling Meadows site. The site specialized in airborne radar and electro-optical countermeasures systems. And after that, he worked as a consultant in the operational test and evaluation of similar systems, primarily consulting for the Institute for Defense and Analyses in Alexandria, Virginia. He first became interested in astronomy in high school, like a lot of people. He completed his first mirror and telescope in 1965. And he was a member of the Detroit Observational and Astrophotographic Association. I thought I'd mess that up. From its inception. And while at Georgia Tech, he was a member and sometimes an officer of the Atlanta Astronomy Club. He planned and supervised the construction of their first observatory. He and his wife, Arlene, reside in St. Charles, Illinois, and are currently members of the Fox Valley Astronomical Society, the Northwest Suburban Astronomers, and the Chicago Astronomical Society. And we're very happy to welcome him here this evening.
Are you ready for me?
I am ready for you, yes.
Okay. Hopefully everybody is seeing the presenter's view. In the, pardon me, the customer's view, not the notes page. Okay, very good.
Yes.
Well, thank you, Jennifer. It's particularly appropriate that this should be co-hosted by Wayne State and the Detroit Public Library. When I was a freshman in the middle 1960s at Wayne, I often did my study hall work in the public library because I could sneak off and read astronomy magazines when I got tired of doing algebra and calculus and group theory or whatever else it was at the time. Arlene did the same thing 2 years later, but we didn't meet until we both were attending a mathematics colloquium in the basement of Prentice Hall, and that was like in 1970. So many fond memories of Detroit, the library, and of course of Wayne State. And with that, we will say nothing more about it. Oh, one thing. The plant I was at, for those of you who are old enough, the plant I used to work at used to be known as Hallicrafters Radio until Northrop bought them. Okay, so this is about the Webb Space Telescope. It is the latest of a series in their Great Telescope series. Moment. There we go. The previous ones, of course, were Hubble, which operated in the near UV and visual range, Chandra, which was a X-ray observatory, and the Spitzer IR observatory, to which the Webb Space Telescope is the immediate follow-on in that sense. It's a deep space infrared IR telescope, and its goal is to mostly look deeply into time, but not solely that. Just a bit of history. The project's named for James Webb, who was the NASA administrator. He led NASA through the Apollo era, and he left NASA shortly before the Apollo 11 launch because he was not in the good graces of the incoming Nixon administration, having been a New Deal Democrat. The project was conceived in 1989, 1994, originally as a $500,000 project, of significantly smaller scale than what it's ended up being. This is not a unique story, both in industry or in government. Through a series of trade studies, they expanded it. They put more realism in the costs, and it was eventually decided that it would be well over $1 billion program. That would be vehicle, bus, optics, the instruments, and the launch. Even that, of course, was optimistic, as you might imagine. They awarded the prime contract in September of 2002 to TRW for a little under $1 billion. And this did not include the costs of NASA for management or for their parts of the work, which are considerable, as you'll see, and some of the associate contractors. TRW was purchased by Northrop Grumman in 2003. This was 4 years after I left the corporation. So I have none of my fingerprints are on this. no guilt or glory. The mirror and the instruments were awarded at about the same time. And the initial launch was set for 2011, but as these things tend to go, both in programs I've run and programs I've monitored for the government, there are always delays in these things. This one was originally delayed to 2017, then 2019, and of course, then a whole series of things happened which were totally outside the control of NASA and the contractors. What are the mission objectives? Well, first of all, the mission has to last 5 years. That may seem prosaic to say it's an objective, but the length of a spacecraft is important. The goal is to last 10 years. Key factor, of course, as is often the case, is the consumption of propellant that are needed to maintain the orbit or the positioning of the spacecraft and the pointing. And the orbit is located at the L2 point in the Sun-Earth system, well over 1 million miles from Earth, which means there will be no servicing mission unless maybe Mr. Musk can do something interesting in the next 5 or 10 years. And the halo orbit itself is roughly the radius of the Earth-Moon orbit. And I'll give you some diagrams to make this a little clearer. The scientific objectives are what drove the design. And this is all I'll say about the science. Everything else will be about the instruments and the testing. But though those scientific objectives drove the design in many ways, in almost every way, actually. First was, of course, to explore the end of the Dark Ages, when the first light could emerge from the ionized clouds that were reionizing. Following that was the assembly of galaxies. That is how they first form out of the intergalactic media. Then on a smaller scale, large by our standards, but on a cosmic scale, the birth of stars and protoplanetary systems. And searching for planetary systems and trying to see if they can find traces of the origin of life in other solar systems. Now, a cynic would say they throw that last one in because they have to. It's like saying you're going to chase dark energy or dark matter. You have to say you're chasing the origins of life, but it is legitimate in this case. The point of this list of 4 main scientific work areas is that they all require high sensitivity to infrared radiation. Basically because the radiation, the photons from the early history of the universe will be heavily redshifted, and also because during planetary and star formation, the fusion is not going on yet, and all you're seeing is the radiation from the compression of the gases or the other materials. And finally, regarding the origins of life, the molecular spectra, the spectra of organic molecules largely lie in the infrared. So you've probably all seen this picture multiple times. This is how it will look when it's fully deployed. It's got multiple elements, and we'll talk about each of those in turn. This picture gives you a sense of the scale of it. This is the telescope with 1/2 of the mirrors folded back, the other half are deployed. The boom that holds the secondary is in its stowed position. And here we see a 5'7" or 6-foot worker. So it gives you a sense of how big this is. It's out at the L2 point, which is an equilibrium point exactly opposite the Earth at the sun, but it's not a stable equilibrium. It's in the sense it's not a gravity well. In a gravity well, which is the case at the L4 and L5 points, for example, if you perturb the object slightly, it will drift back to the equilibrium point. In the case of this, it's an equilibrium point, but it's unstable. So the way it maintains the stability is to execute what's called the halo orbit. And that's approximately to scale relative to the radius of the moon's orbit. What is L2? Well, as I said, it's a semi-stable point of orbit. It's a point, as this diagram shows, in which the centripetal acceleration is balanced by the gravitational pull of the Earth and the sun combined. These were first identified in 1772 by the Italian-French mathematician Lagrange, shortly after the time of Newton. And anybody who studied advanced mechanics will, of course, remember the Lagrangian formulation of classical mechanics. As we said, it's unstable, so it uses this halo orbit, which means it needs propellant to do that, which becomes one of the limiting factors. This is not the first time the L2 point, the Earth-Sun system L2 point has been used. There are in fact currently 2 satellites there. And as I said before, the distance of the L2 point from the Earth is about 1 million miles, a little over 1 million. And in fact, it's going to take the JWST 30 days to reach it, during which it will be extremely busy, as you will see in the deployment videos. It's a very large spacecraft. And in fact, even with its mirrors folded up, it barely fits inside an Ariane 5, which at the time the program was starting was the largest available lift vehicle. To reach the Lagrange point, it's best done with as much centripetal acceleration boost as you can get on the Earth, and that's near the equator. So the fact that the European Space Agency launches the Ariane 5 from French Guiana helps. And as you can see, the outermost 2 sets of segments of the mirror are folded. So here are the major components we'll be talking about. There's the optical telescope element, or the OTE. There's the primary, the secondary, and what's known as the aft portion of the OTE. There's the integrated science instrument module, the ISIM, the sun shield, which protects the instruments from the heat of the sun, and then the bus that contains the majority of the processing, some of the cryo coolers that are used to cool some of the instruments, and the power system. Stuck off the back down here is the solar panel, and this is the momentum flap, which is used to help control the momentum of the vehicle, the rotational momentum of the vehicle. When you look at this and you realize it's in raw vacuum space, you realize this is a great solar sail, and maintaining the orientation of the spacecraft when it's being pushed, in many cases, the orientation won't be perpendicular to the sun even. So it'll exert considerable, the solar pressure will exert considerable torque on it, which has to be counteracted, which is the function of one of the systems in the bus. But let's look at the optics first. I mean, I, as recently as 2013, was still making mirrors. This is the size of the JWST primary mirror compared to the Hubble. The Hubble was a single disc of quartz, of optical quartz. It had a suspension system, but by comparison to the JWST, it was simple. The JWST is composed of 18 segments. If you look around the periphery, you'll notice that there's a certain radial symmetry. This segment, this segment, this segment, and so on. Every other segment in the outer periphery are all at the same radius from the center. So they have one curve, one figure. The alternating ones have a different figure. And finally, the innermost ones have a third figure. So they all are slightly different. So why is it so big? What's this appetite for giantism? What drives it? Well, it's the fact that you're dealing with infrared. There's 2 sets of, actually 4 instruments. They fall into 2 classes. There's instruments for the near IR and the mid IR. The near IR is from slightly above visual, 0.6 micrometers, up to 5 micrometers. Then the mid IR goes from a little bit below, there's overlap, 4.9 to 28. For comparison, green light is 0.55 micrometers. Well, IR wavelengths are longer, and the resolution of an optical system is the ratio of the wavelength, is proportional to the ratio of the wavelength divided by the diameter. So if you multiply the wavelength by a factor of 10, which is the case right here in the middle, you have to have 5 times bigger a diameter. Similarly, IR photons are less energetic. The energy of an individual IR photon is going to be, of any photon, is proportional to 1 over the wavelength. So if you double the wavelength, you reduce the energy of each photon by half. And therefore you need a greater mirror area to feed the detectors a reasonable signal. Now the JWST compared to the Hubble, it's only 2.7 times the diameter and 7 times the area. Ideally, you would want it to be at least 10 times the diameter and 100 times the area. But that wouldn't fit in even the Ariane 5. So you do what you can. And you make up the difference with better detectors and with cryo cooling and everything else you have to do. So the key technologies of the optical system and parts of the others, it's a multi-segment beryllium mirrors. Beryllium is chosen because it has a very low coefficient of thermal expansion, and it is also extremely light. And this is not news. There are other systems that have used beryllium mirrors. If you were to go pick up any book since the 1960s or maybe earlier on optomechanical systems, you would find beryllium mentioned as an alternative. There are actuators behind each of the segments that are used to fine tune the optics once it's in space. It's designed to be perfect with no fiddling with those, but there are error tolerances involved in the real world, and those allow the system to be adjusted in real time. It's an interesting optical design. It's called a folded Baker-Paul design, 3-mirror design, 3 active mirrors. It uses something, this was a NASA invention called micro shutters. Basically, over each of the pixels of some of the detectors, there's a little shutter that opens up to let the light only hit the pixels that are selected. This is done so you can actually look at an object that's adjacent to a bright object and not be overwhelmed by the light from that adjacent object. I should mention, all of us buying digital cameras or cell phones, those manufacturers are all in a race for smaller and smaller pixels. That's so they can make their cameras smaller and smaller. Well, in the infrared, to get good signal to noise, you actually want larger pixels. So instead of having a 2-micron pixel like some cameras have, terrestrial cameras, these things have 9 or 18 micron pixels. A micron is a thousandth of a millimeter. So the micro shutters are a NASA invention that are used to determine which pixels actually get exposed and to reduce scattered light and blooming. And it's got this multi-layer solar screen. And the purpose of that, of course, is to shade the spacecraft from the heat of the sun and even the backside of the Earth. And the reason for this is it wants to hold the upper section above the sunscreen at 40 to 50 degrees Kelvin, which is approximately minus 390 Fahrenheit, if I remember right. So it's trying to hold it at a very cold temperature. On the hot side of the screen, it's something in the order of 600 degrees Fahrenheit. And that's the sunscreen I was just talking about. It's basically a multi-layer thermos bottle. But we're going to address for the moment the optics. So here's the 18-segment primary mirror, the secondary mirror. That's only a foot. These are about 4.5 feet, as you can see. That's one of the primary mirror segments on the test stand. Everybody you're going to see in here is going to be dressed in a clean room suit. And then this is the tertiary mirror, which we'll talk about in a second, and then the so-called fine steering mirror. Superficially, this looks like what's called a Cassegrainian telescope with a concave primary and a convex secondary, but it's a little more than that. This is my sketch, so if I got something wrong, it's not NASA's fault or Northrop Grumman's or Ball Aerospace's fault. So the light comes in from the star or the galaxy or the molecular cloud and hits the primary mirror. I didn't draw, of course, all the light paths. It bounces off the secondary mirror like in any good Cassegrainian, but then the two paths cross and it hits the tertiary mirror. And the tertiary mirror really corrects the optics and produces a flat field. So it's a flat field, does not need a field flattener like the Hubble did, no auxiliary optics other than the tertiary mirror to fix it. And it's called tertiary because it's the third mirror. It bounces the light forward where it hits what's called the fine steering mirror, which makes microscopic adjustments to the pointing of the entire telescope. And that sends the energy into the integrated science instrument module, which is where all the detectors, all the cameras are. And here's a picture actually of the Aft Optical Telescope assembly unit. And this is looking into it from the front. There's the tertiary mirror tipped, and you can't see it, but the fine steering mirror is behind, on the other side of this baffle. The primary mirrors are held in this frame. This is actually an engineering mock-up. One of the things when you build a system like this is you don't just build the system and put it together. You typically have to make boilerplate or brass board assemblies to mount and fixtures to mount things to for integration and test and development. So this is not the actual backplane. This is actually a mock-up of the backplane used to hold things during engineering development. The primary mirrors, there's 18 segments, as I said, and they're all this hexagon shape. Just the processing of these alone took many trips around the country. The initial blanks were pressed out of powdered beryllium by Bush-Wellman, located in Ohio. That required very special handling since powdered beryllium is toxic. produces a condition known as bilhariosis in the lungs. So they had to press it under very controlled conditions to create the blanks, the rough shapes. They were then sent to Axis Systems in Alabama, which, as we say in the optics world, hogged out the rough shape and cut the rear webbing into the back to lighten it. And I'll show you that in a second. From there, it went to SSG Tinsley. Tinsley is an old-fashioned telescope making company. You can find their ads in Sky and Telescope in the 50s and 60s. They did the grinding, the fine grinding and polishing, and the first pass at the figuring. And again, there were 3 different optical prescriptions required. They then went to Ball Aerospace in Boulder, Colorado, who put them in a cryogenic chamber and actually tested them. And then they passed their test data back to Tinsley, who did the final tweaks on the figure. And last but not least, they went to quantum coatings to be coated in gold. Why gold? Because gold reflects virtually all the infrared radiation, whereas the normal aluminum that we use or barrel metal that we are used in most coatings for telescopes in the visual or UV range don't work in the IR. So it has to be gold. There's only, I think, about less than 4 ounces of gold, I think, on this entire assembly. It's microns thick. Oh yes, the accuracy of these mirrors is of the order of 10 microns, which would be a fraction of a wavelength of visible light. So they're extremely precise in the IR range, which has longer wavelengths. Here's one of the examples. This is the back of one of the blanks before it's being processed. Notice all the webbing that was cut out to lighten the mirror even more. This mirror assembly this mirror is not even 40 pounds. If you look closely, you can see there's funny little circles that look like attachment points, and that's what they are. The mirrors are not mounted directly to that back plane I showed you before. They're actually mounted to a beryllium delta frame. These orange points are where it's actually attached to the large back plane I showed you for all 18 mirrors. The delta frame is then attached to these wiffle trees, which anybody who's built an amateur telescope that had a bigger mirror would recognize this arrangement. What they wouldn't recognize is the use of a hexapod, which means 6 actuators. Each pair of actuators are used, and these are used to adjust the tip tilt of the optical elements when they're installed, which is a major part of the commissioning of the instrument, which will take a lot of time, we'll learn. Finally, there is 1/7 actuator that attaches to the center that is used to pull or push on the mirror with these struts, and that is used to very slightly adjust the focal length of the entire mirror, so that all the mirrors come to a common focus, both in the plane and in depth. Okay, spacecraft bus and sun shield. The spacecraft bus, remember, is that box that's below the thermal screen. It's responsible for some pretty prosaic things, actually. Electrical power with a solar panel, communication system, that's obvious. You're going to have to talk to and from Earth. We operate, of course, a deep space network here in NASA in the US, so we can reach it any time of day. There's a command and data handling subsystem that talks to the instruments. There's a propulsion subsystem because, again, it has to perform station keeping operations, and it has to be able to change orientation to point at different parts of the sky. And of course, a thermal control subsystem. I skipped over the attitude control subsystem because it's actually fairly sophisticated. As I mentioned before, the solar shield is a wonderful sail, and the light pressure will not always be perpendicular to the sail. Sometimes the telescope might be looking over here relative to the rays of the sun. In that case, there's going to be torque exerted on the shield, and you have to compensate for that. And that's done with something called the momentum reaction wheels, which absorb that momentum. And they can only do it to a certain point, and then the attitude control system has to, in the words of NASA, dump the momentum by executing a actual rotation of the platform. They typically plan the schedules at the Telescope Space Institute so that they minimize the use of the propellant for only dumping the momentum of the reaction wheels or moving the orientation. They try to combine the two wherever possible. So there's a great deal of mission planning that goes on at the Space Telescope Institute to control this system properly. And it's got autonomous safeguards so it can't go out of control, and to minimize the use of propellant. And here's the spacecraft bus, an engineering drawing. Here's this sticks out the back. This is the solar panels. These are actual heat radiators, and I'll explain why they're there. And the reaction control engines are actually down here and on the other side. This is actually the spacecraft bus getting ready for integration, and you can see how large it is. And of course, it's wrapped in gold leaf. It reminds us of the Apollo days. This is the sun shield deployed. It had to be deployed multiple times, of course, in the test phase of the program. It's about the size of a tennis court, and it's made out of Kapton, which is a plastic used for thermal isolation and insulation. It's coated with aluminum and silicon, and there are 5 layers of it. So think of it as a 5-layer vacuum bottle, 5-layer vacuum bottle. And again, there is no atmosphere to conduct heat around it. So the only way heat can be transferred from one level to the other is through radiation. And that's why it's silver. And the bottom layer, of course, you try to keep pointed as much as possible towards the sun so that the optical instruments, which will be up here, are in the shadow. And here we see the 5 layers. The thickness of these is between 10 and 25 microns, a fraction of a wavelength. Pardon me, a substantial fraction of a wavelength. Okay, there are other videos out there you can find for the deployment, and you can Google them very quickly and find them in YouTube. I wanted to capture this section because it shows the deployment of the sun shield. At this point, the solar panel has already been deployed, and the antenna, the downlink antenna, has been deployed. The spacecraft has already reached beyond the orbit of the moon, so it's further than any human being has traveled. So first it deploys the forward pallet. Hopefully you can all see this. This is occurring 3 days into the mission. And just that deployment took over an hour. Now it deploys the aft boom. So now the aft pallet is deployed. The actual sun shield is still in a protective cover, which we'll see opened up next. So at 4 days, 15 hours, the tower actually deploys to get out of the way for the rest of the sun shield deployment. This also creates extra clearance for the telescope, thermal clearance. Remember, the whole point of the sunscreen is to take 600 some odd degrees Fahrenheit on this side and turn it into minus 390 Fahrenheit on that side. So now we're at 5.5 days. And now it's deploying the booms to the side and pulling the screen with them and popping out heat radiators, which are used to dissipate heat from the electronics in the bus. Notice that they are, of course, on the hot side. You don't want them on the cold side. They would mess up the instruments. Okay, now it will begin to stretch the 5 segments out. It tensions it and starts moving it up. This entire process requires over 170 actuators and latches to operate correctly. So you can well imagine it was tested. This is now the momentum flap. This is part of the attitude control system. Think of it as ballast, if you like, or as a rudder on a boat. You can see here some of the reaction control system motors. And now we're at 6 days. So it's taken over 3 days to get us to this point. 10 days, they start the cryo cooler, which I'll talk about when I talk about some of the instruments, which we're going to do now. I put this slide together because I can never remember who did what to who. This is the one in which I'll give credit to the people who made these various devices. There's a near IR camera by University of Arizona and Lockheed Martin, a near IR spectrograph by European Space Agency, contracting with Airbus Industries in Europe. near IR imager and slitless spectrograph by Canadian Space Agency with Honeywell, international with collaboration by the University of Montreal and the Royal Canadian Research Council, excuse me. And the mid-IR instrument package, which was a joint effort of a European consortium and the Jet Propulsion Laboratories. And if anybody asks me later who did what to who, I'm going to point you back to this slide. Okay, so here's the instrument package, which contains all these gadgets. This bolts at this point to the back of the optics that we talked about, the main mirror. Okay, so let's briefly go through each of these cameras and what's in them. The near IR cam, which will be the only thing that will produce what most of you would recognize perhaps as Hubble style pictures. The rest of them, with one exception, I take that back, but there is another one, but this will probably produce a lot of the pictures you'll first see. It's got dual redundant modules with 2 sets of cameras back to back, and each camera has 2 separate sensors in it. Each region imaged by the modules is 2.2 by 2.2 arc minutes. That's about 1/12 of the diameter of the moon. So it's going to be looking at a region of space about 1/12 of the diameter of the moon. The image regions will be offset by 44 arc seconds, and an arc second is 1/60th of an arc minute. So there'll be a very slight offset between them. And each module will image 2 bands, which is why I said there's actually 4. One band will be 0.6 to 2.3, and the other one will be 2.4 to 5. And that will enable you to do a temperature comparison between the radiation for the same object at this band and at that band. Basically dual color temperature sensing. So this is what it looks like. Notice it looks like a mirror image. That's because it is. This is about 1 meter across, maybe a little more. This is sitting on a big optical bench here during testing. Here it is sitting in a frame for the technicians to work on it. This large structure here is the filter wheel, and these are the 2 camera modules. And this is pretty much what it will produce. There's a module in each pair of cameras, one on the top, one on the bottom. So there's 2 sets of these. And the total field of view will be 5.1 arc minutes in these 2 distinct windows. So again, the pixels, in this case, there's 4 megapixels in each one of these sensors images, and they are 18 micron pixels, quite large. And again, that's done to improve signal to noise. The other instruments, by and large, are spectrographs. So I thought I'd give you a quick tutorial on that. A spectrograph is an instrument to split light. It could be X-rays, UV, visual, IR, radio, into individual wavelengths. And the purpose of it is to allow the scientists to determine objects' chemical composition, redshift, temperature, and other things. And basically what a spectrograph does is it takes the light coming in, which is a merged composite of many wavelengths, and splits it into these multiple pieces using either a prism, like Isaac Newton showed us, or an interference grating. And these interference gratings have been around since the 20s or 30s. So it's well understood technology. And in fact, if you want to spend $50, you can buy a very nice one from Edmunds Optics. Thanks to Scientific American, there's a nice, simple, generic picture of what a grating spectrograph looks like. The light from the telescope comes through a slit. However, one of the instruments is a slitless spectrograph. It goes through a mirror that collimates it into parallel light. It bounces off the grating, which is what splits the light into the different colors. There's only 2 beams shown here because that's the edge, but in fact, a ray that comes through the center would produce a similar fan. And this mirror here then focuses all the rays for a single color on a single spot on a detector. And the result is you produce an image like this, or you produce more accurately, you would of course produce photon counts in the detectors, in the digital detectors. So that's basically the concept for all the spectrographs. I will make one comment. The resolution you achieve, how far away the red is from the blue, is determined by the focal length of these instruments. And therefore, to get high resolution, you need a long focal length instrument. Well, you don't have a lot of room in a spacecraft. So you'll see when I show you the diagrams that the optics are all folded. It looks almost chaotic, but it's done for very good reasons. So the near IR spectrograph is the one that actually captures multiple spectra using microshutters. It can do up to 200 simultaneous spectra in a 9x9 arc minute field. Now, 9 arc minutes is about 1/3 the diameter of the moon. So it can, if there's 200 objects packed in that they want to shoot, they can actually capture the spectra with this, of all of them simultaneously, which is a huge efficiency. It can also simultaneously do a single high precision spectrum. It can even do spectra of extended objects. To do that, it can't use the other two functions. It can basically take the image of a 90 by 90 arc second object, say a distant galaxy or a small patch of a nebula, and actually produce a spectrum for every single 10th arc second patch. A 10th of an arc second is the resolution of a 40-inch telescope. So that's very high resolution with being able to capture spectra. This is what it looks like. It's very daunting. It sits on an optical bench. And this is the, I won't show you this. I'll show you the engineering drawing, but this is what it looks like. The one thing I will call out is this object, which is a wheel with gratings on it, and each grating is cut to optimize the spectra in a specific wavelength region. This is a little more friendly drawing. The light comes through, the IR radiation comes into the ISM and is pumped into this coupling mirror, which then sends it into this focusing mirror, which then bounces it off this mirror, which sends it through a filter wheel, which screens out undesired radiation. It then bounces through another series of mirrors and eventually makes its way to the grating and into the camera, where all the other stuff I talked about earlier is. These are the micro shutters. These actually sit on top of the pixels of the sensor. There are 4 sensors in each one of those cameras. Again, remember, there's 4 of them. And the result is, this is laboratory data, and the result is you'll produce something like this. So in a single capture, single dwell on a patch of space, these are all individual spectra of different objects. And here we'll show you what the optical path actually looks like. So bear with me on this. Again, this is a product of our colleagues in Europe. So here's the light beam coming into the ISM, and then this mirror directs it into the camera. This is that fold mirror you saw at the beginning. It bounces off this focusing mirror, which narrows the beam down, bounces off that mirror, then into the filter wheel, which is programmed for the desired object. The little spherical object at the bottom, by the way, is a calibration source. It passes through the field sensors, bounces off yet another mirror, and now the beam is expanded because you want to spread the spectra as much as possible. The selected grating is hit, bounces off another turning mirror, and then another dispersion mirror, which spreads the spectrum. The sensors are in that brown housing. And now it goes into zeros and ones. These sensors are kept at a nominal temperature in the range of 40 to 20 Kelvin. They're not super cooled because they're for the near IR. Okay, next instrument is the IR imager and slitless spectrograph. It looks at a 2x2 arc minute patch. Again, that's about a 1/12 of the diameter of the full moon. And it enables you to do surveys with low resolution spectra. This is a product of our, well, I'm not going to say, I think it's our friends in Canada. I think I got them in the right order. It's got a very simple optical bench compared to the earlier ones. So here's the columnator. The light comes through a pick-off mirror, goes into the columnator, and then goes through the filter wheel and goes into the detectors, the camera. This is a diagram of that optical layout. And again, the reason it's folded is to get these long optical throws to produce a reasonable amount of dispersion in the spectrum. And this is a look with part of the covers taken off. So there's the big filter wheel right in there. And lest we forget, on the other side, if you look at this picture, you see that the mounting legs are here. Those are the mounts that attach it to the ISIM structure. On the opposite side of that mounting plate is actually the fine guidance sensor. Anyone who's done astrophotography knows that you can't count on a telescope to stay exactly on the stars. Something is going to happen. In the case of the Earth, of course, you've got this atmosphere you work through, you've got imperfections in your gears, you have all sorts of things that you need to make tiny little fine guidance corrections for. And Hubble had to do this too, and so does the JWST. And so it's got an actual pair of cameras that are used to do the fine guidance function. And these will actually track to an accuracy of something like a 20th of an arc second, which is very good. It's sub-pixel for the sensors. And this has actually been tested at cryogenic temperatures in the chamber. We'll talk about that at the very end. Okay, now we're coming to the Queen, the premier instrument of the JWST. The IR instrument package. It covers the region in the mid-IR from 4.9 to 28 microns. It's the most demanding because they're the lowest energy photons, 28 microns. So each photon has approximately 1/50th of the energy of a visible light photon. And that is what drove many of the elements of the design, whether it's the size of the mirrors or the thermal management. Remember, above the sun shield, you're at 40 to 50 degrees Kelvin, which is very cold, roughly minus 390 Fahrenheit. But to make this type of sensor work, you need to go down to liquid helium temperature, which is approximately 7 degrees Kelvin. It does this with what's called a Stirling engine-based cryocooler, the little electric Peltier coolers you use that we amateur astronomers use, and that are used to cool beer in RVs. Won't work. You have to go to a Stirling engine. And because of that, the design had to be partitioned into 3 thermal zones. You couldn't put the Stirling engine close to the sensors. I apologize for this, but it's the only way I know to describe it. Down in the base of the bus, where you're on the sun side of the sun shield, is where the cryocooler lives. And it cools that, it actually compresses the helium down. It goes through region 2, which is still below the sun shield. These are thermally isolated from each other, and where some of the control electronics and the processing unit live. And it goes through that section and goes through up into the ISM, which is in the 40K region above the sun shield. And there is where you actually have the optics and sensor module for the millimeter wave, the medium intermediate millimeter wave optics and sensors. And only the sensors are cooled. So just like in your refrigerator, it expands at this point, the gas is 17 or 18 degrees Kelvin. It's expanded and that cools it down, and that cools the sensors. And those sensors then have to be thermally isolated from the rest of this structure, which is at 40K. So they had to very carefully partition this system to do that. I apologize for this, but it shows what's actually going on. Here's the compressor and the cryocooler. It's down inside the bus along with the intermediate stages. And then this final section that goes up to 18K and drops it to 7 to 6K in the actual sensors is here. And this generates a fair amount of heat in the cryocooler, which is part of the reason why you had those heat radiators. You needed those heat radiators we talked about earlier to dump energy out of the electronics, but the cryocooler produces much more. The IR instrument actually has 2 modules in it. There's an imager, and there is an imaging spectrometer, and then there is a pure spectrometer. This is the cryocooler. It's quite large. It's about 3 feet long. And it has moving parts, and it has to run constantly. So it had to go through extensive testing to make sure that it would not fail after just 1 or 2 years into mission, because it has to run. If it doesn't work, then the mid-range IR sensors systems are not going to function. So this is what the mid-range IR instrument package actually looks like. It's got 2 separate detector systems in it, one for the imaging and non-image spectrometer. And finally, the ISM with all of its packages was completed its first round of testing and assembly in March 2014. But subsequently, it had to go through more testing. So the individual instruments had to go through their own extensive test programs. The test specifications for those instruments was a flow down of the entire system. And of course, when you do the testing, you find things to fix. In fact, my experience with test programs, both as a contractor and as an oversight person, if you have a test program that doesn't uncover something, I frankly wouldn't believe it. It would be a miracle, at least in the first round. Very often you have to go back and resolve issues you see, however minor, and then retest them, because any deviation from expected performance has to be understood. You can't just say, oh yeah, it's good enough. And that brings us to the overall topic of integration and test. Or as we used to say in my old work, this is where the rubber meets the road. So it's especially critical, of course, for the James Webb Space Telescope. There's only one being built at a huge cost, and there's no repair concept. Most of you might remember the problem that Hubble had where the mirror system was not correctly tested. It should have been adequately tested, but the testing was not done correctly and interpreted correctly with enough management oversight and technical rigor. And so they launched a mirror that actually had a serious flaw into it, and it took several shuttle missions to actually fix it. That is not possible with the JWST, so things have to be done right the first time. And of course, you've got integration of components from multiple sources and agencies, which adds complexity. It's manageable, but it adds complexity, and you have to be careful. Oops, I think I missed something. No, I guess not. Okay, so the first thing you do is you test the subsystems. The examples in this case are the ISM, the bus, the individual instruments. They all have to be tested. And the way this is typically done in the aerospace industry is you have vacuum and temperature chambers with vibration tables. And that's particularly important for the launch environment with the JWST. There's very little vibration once it's deployed in the vacuum of space, and it's moving very slowly with elegant ease. The launch is a different matter. The launch environment is a different matter. So you would typically flow down these requirements, and for the subsystems, standard aerospace vacuum and temperature chambers and even vibration tables are available that you can do this with. That's not true for the completed system, nor is it true for the optical performance at cryogenic temperatures. There are no standard chambers that you can have. I once had to consolidate operations of several divisions in my old company, and the first thing I did is I would grab the test chambers from the old division that we were merging. So to do completed system testing, you had to have special facilities. Fortunately, temperature, vacuum, and vibration decouple in this program. Vibration, as I said, is most severe by orders of magnitude during the launch process. And of course, you've probably heard the term max Q, that's maximum dynamic pressure on the launch vehicle. There's crosswinds and there can be buffeting. And while the JWST is protected by a shroud from direct impact with the upper atmosphere, it is subject to energy transmitted through the structure of the spacecraft, of the launch vehicle, into the JWST. And of course, when you're near the ground, there's vibration and acoustic noise from the first stage engines firing, which can be quite severe. Fortunately, these are all close to nominal temperature events, which allows you largely to decouple the cryogenic temperature testing from the vibration environment. Just to show you, they don't make this stuff up. The Ariane 5 users manual, which you can find online at the ESA's website, actually gives the acceleration profile, how much you're pushing on the spacecraft under the shroud vertically along the launch direction, how much longitudinal and lateral vibration there is. It can be up to about a G, at numbers like 100 hertz. So 1 G doesn't sound like a lot of force, but you're bouncing back and forth at 1 G. So it's fairly severe environment. And then there's acoustic noise, and that has its own profile, of which the peak occurs at just about 100 hertz. So what they selected was basically the 5 to 100 hertz region for most of these tests. Again, this is not the operating environment. This is the launch environment, which means you need the JWST to be buttoned up. So once you're in deployment, like that video I showed you of the shield coming out, now you're in a hard vacuum, but it's low vibration. And it's either hot because the sun's hitting you, or you're in shadow and it's cold. Now, these are things that NASA's used and their contractors are used to dealing with it. And of course, there is this cool down process during the voyage to L2. And then all during this deployment, there's this variable temperature regime going on, depending on whether you're in the sun or not. So the individual systems have to be tested for hot, cold, vibration, and noise individually. Those are survival tests, not operational tests, because they're not operating during the launch process. So one example here is, here's the mid-IR instrument package. It's going into a big vacuum cryo chamber at Goddard Space Flight Center. The thermal shield, which will sit on top of it to protect it from the heat from the other instruments, is put in place. Here's the near IR spectrograph, and it's being put on a testing jig and instrumented with stress and strain gauges and accelerometers trying to go into acoustic noise testing. And then finally, the complete instrument package, the ISIM, the entire thing that's bolted to the back of the optics, is placed into this cryo chamber. I think they pull these technicians out with harnesses. I don't think they let them climb up a ladder. And they probably pull the ladder out with at least 3 straps attached to it. You wouldn't want it falling back in. So as I talked, the individual subsystems, they get their individual testing and qualification. It's then integrated into the ISIM, which was done in 2005, I believe, 15. The optics are integrated. And now the optics have to be tested at cryogenic temperatures, which we'll talk about. Then you need to test the deployment of the system. And then you need to integrate the two, button them up in the launch configuration, and perform vibration and acoustic noise testing on that, because that is when the package will be subjected to that environment. The acoustic noise and the vibration is during the launch. And that's the configuration for launch. So what were these Phillips system tests? Well, there was the vibration acoustic noise testing that was done from 2016 to 2017. It required a new shaker table to mount the JWST to. And then the optics themselves were tested in a space environment in 2017. Again, they did not want a repeat of the Hubble experience because Hubble was not tested as a full-up optical system. So for the shaking, for as we used to call it, shake, rattle, and roll, they had to build at Goddard Space Flight Center, had to build a customized stand. This is a large magnetic shaker, basically a large solenoid. You would put 5 to 100 hertz AC through there at 360 kilo. In other words, almost 1/3 of a million volt amps, watts, if you wish. That generates 50,000 pounds of force. This shake table is approximately 6.5 feet high. You can see the ladder. The JWST mounts to it with a fixture. You don't want to put the package on top of this without fastening it somehow. And the mounting fixture has to be representative of the attachment adapter used in the Ariane 5. So those two together were roughly 7,000 kilograms, or roughly 15,000 pounds, 8 tons roughly. Here we see the buttoned up JWST. It's completed. It's gone through its piece part subsystem testing. And it's in what they call the mobile clean room, and it's being lowered onto the adapter plate, to which it will be fastened and then torture tested. For the optical testing, there was only really one facility available, the Test Chamber A at Houston. This was originally built for the Apollo lander testing. You could put an entire Apollo lander inside it. It's been on the National Registry of Historic Places since 1985. So it was a monument, and it had to be demonumentized, so to speak, to do this testing. When they finished it, they put it back in its original configuration and put the plaque back on. And it had to be significantly refurbished and used to test the JWST optics. And so this is the diagram. Here's the JWST looking straight up into the test rig, which generates infrared energy. The actual instruments are down here for the testing, along with the fine guidance sensor, for example. This entire package, you can see how large it is. This is the door. This whole thing can go down in the interior, can go down to below 20 degrees Kelvin. It only needed to go to 40, of course, to simulate the payload temperature above the heat shield. This is the structure that actually held the IR beam analyzer that are used to test the complete optical system. You can well imagine before they mounted that in the chamber, they went over it with a fine-tuned comb looking for loose wrenches, screwdrivers, anything. Foreign object detection is a high priority with a program like this. The stats on this test chamber, it's 55 feet tall, 90 feet tall, 55 feet in diameter. The door is 40 feet in diameter and weighs 40 tons. It can cool down to 20 degrees Kelvin. They had to add a helium shroud to get it down that far. And this is done so that you can operate near the operating point of JWST, which is nominally 37 Kelvin. You'll hear numbers like 40 and 50 in various places. It pumps down to space vacuum, which is 1/10 of 1/millionth of an atmosphere. And it takes a month from the time you close the door till you reach the test condition, the 37 degree, the 20 to 37 degree Kelvin environment with 1/10 millionth atmosphere. It takes a month of cooling and pumping. Here we see the trolley on which the JWST was mounted and rolled in May of 2017. Here's the JWST mounted on it. These are protective carbon fiber covers, which are used when transporting the device. You don't want to drop something on it. It shows the secondary mirrored in the deployed condition. So they completed the chamber testing. They ran, after they cooled it down for a month, they tested it for 93 days nonstop. Once you get the chamber pumped down and cooled, there's no reason not to keep going 24 hours a day. So they had to swing triple shifts of engineers and technicians to keep this thing going for those 93 days while they executed their tests. And they completed the entire optical testing and the vibration testing I talked about in December of 2017. And of course, they found some issues. That's normal. Again, I wouldn't believe a test program if it found no issues. The question is the severity and how much retesting you do or regression testing. And they had planned the launch for the spring of 2019. Of course, there's always something that intercedes, and in this case, it's life. The schedule was predicated for 2019, was predicated on being able to fix things in the normal way. Well, COVID-19 put a stop to that in late 2019, early 2020, so that the testing slowed down significantly. And then the Ariane 5 in 2019, 2020 experienced some non-catastrophic anomalies with the payload shroud separating. And while those may have been non-catastrophic for those missions, those two missions, caution would say that you want to make sure it's understood and fixed, and at least one or two, in this case two, more Ariane launches done in which there are no shroud anomalies. Because a shroud anomaly that might not damage, a smaller satellite or a communication satellite could be catastrophic for the James Webb Telescope. So that pushed the launch date to March 2021, and then finally to December. And again, you can't change this launch date just at random. They have to coordinate a long time because ESA, European Space Agency, is flying other vehicles. They have to have systems in place to handle it. It's not something you're going to throw a switch and say, oh, gee, we're ready this week, let's go. It has to be planned in a thoughtful way. And so it shipped this September. The exact date was not disclosed for fear, believe it or not, of piracy. It went through the Panama Canal from the Northrop Grumman plant in Los Angeles, through the canal and to Karua, French Guiana. And the launch will occur on the 18th. And with that, I have a video of showing the complete deployment sequence, but I don't recommend we do it. It'll consume too much time. There'll be none for questions or follow-up. There is a, if you Google JWST deployment, you will find several videos on this, and there's a very good one by the most recent one by NASA and Northrop Grumman, from which this is a single frame. Of course, the most stressful time for everybody after the launch is going to be the deployment sequence. It takes 20 days to reach it, and I believe the schedule is nominally 100 days to go through the commissioning process. That's not excessive considering the complexity of this instrument. You know, they think you launch something and it's going to work. Well, in the case, for example, of JWST, they've got to tweak those mirrors. They've got to verify the sensors are working properly. They do some internal calibrations. So there's something of the order of 100 days of the commissioning of the satellite. And of course, the launch and the deployment are going to be the most stressful time for the people at Mission Control, the Space Telescope Institute in Baltimore, and of course, the contractors. One can only hope everything goes well for the sake of course, the taxpayers, but also the people who have invested, the scientists, of course, who are, are eagerly looking forward to the data for this. And of course, the people who've spent several decades of their careers working on this. For example, the program manager, vice president for Northrop Grumman, Scott Willoughby, he's been on the program ever since it started. He's spent a significant portion of his life. The same for almost everybody who's worked on this job, both at NASA and the contractors. They've been on it for a long time. They put a big hunk of their lives in it. So if nothing else for their sake, I hope everything goes well, and fingers crossed for December and for the subsequent deployment. Okay, references. You can find a ton of good stuff at the NASA official JWST site. The Space Telescope Institute will tell you a great deal about the instruments. If you want to know everything about how to launch an Ariane 5 and what it takes, there's a user's manual at the ESA website, and it's dated October 2016, so it's pretty current. And of course, the contractors, NASA, the Canadian Space Agency, and the European Space Agency. Somehow I transferred those last two. My dyslexia got me on the last two. They have lots of things on their Flickr sites. Lots of interesting pictures to look at. But if you go to the Space Telescope Institute, you can actually find much more detail on the instruments than I've given you. There's even user manuals for how to use the instruments and how to plan your operations. If you're so inclined to do a paper exercise on what a scientist would do getting ready to use these instruments. And with that, I believe I am done. So over to you, Megan. If you don't mind, and Jennifer, I can leave this up in case people have questions that relate to particular slides.
I think great up is a good idea.
I can tell it got dark out while we were gone because I'm suddenly in shadow. So, well, it's my Halloween person. There I go, lit up a little bit better. Thanks. This was a great talk. This was really interesting. And I know from the questions that we got that there are a lot of technical people here and some novices too. So lots of interesting questions for you about this. I'm going to sort them into three categories for you. The first ones are the technical questions about the equipment and the testing. Second one's more overview about the web and where it's going to be in space and that kind of thing. And then the last are a few science questions, which I'm not sure if you'll have the info on or if we should save those for Dr. Cackett.
Well, the rules are, of course, I will answer something, and if I can't, I will try to point you to where you might be able to find the answer.
Great.
And
okay, so let's see what order to put these in. One of the questions about the technicality, which you talked about a little bit, but I just want to repeat it as a direct question, is how did they make the mirror larger but less massive than they did for Hubble?
Well, yeah, okay. The Hubble mirror is a single structure. It's actually honeycombed in the back. It's per square meter of surface area, the JWST mirrors are lighter because they're made out of beryllium. And beryllium is extremely lightweight. It has very good thermal conductivity. And they hogged out the back. I showed you that web structure. Let me go to that slide if I can. Bear with me one moment. There. No, that's not it. Here we go. Okay, you see this web structure, that probably reduces the weight by at least 60%. And beryllium is a very light metal, whereas the mirrors, the mirror for the Hubble is made out of quartz, optical grade quartz, and it's much denser material. The full mirror, the full primary mirror for all 18 segments combined, those weigh more combined than the Hubble mirror does. But per square inch, this is, I don't know the exact number actually, but it's lighter, probably by a factor of 2 or 3 or more. So the reason it's lighter is because of the material it's made out of.
Right.
And the fact that it's hollowed out in the back very aggressively, which you can do because beryllium is quite strong. It's light, it's strong, it has low coefficient of expansion. The only real downside of beryllium is when you're processing it, it can be highly toxic. Once it's finished, it's not. But at the time you're processing it, you have to take a lot of precautions.
Got it. Okay.
We used to use it for heat pipes, and the Air Force told us to stop doing it because of they didn't want their maintenance people having to worry about it.
Oh, okay. Wow. Okay, so another technical question. Even though they couldn't test the deployed shield in the cryogenic vacuum, were the deployment mechanisms tested in the cryogenic vacuum to make sure that they would function?
That's a very good question. I would assume so because they would typically do a flow down of testing. I don't know the answer to that exactly, but I think the questioner has answered the question for him or herself. You could probably find if you dig into the NASA website, you might be able to find the answer. I have a very strong suspicion it would be yes. It would be hard to imagine them not doing it. In fact, they'd have to test it not just at cryogenic temperatures, they'd have to test them across the whole temperature range, because before the deployment and during the deployment, the bottom is at a very high temperature and the top's at a cold. So they would have to cover them over a very broad temperature range.
Got it. Okay. Good. Well, hopefully, presumably they did that, but
I'm sure they did. Like I said,
yeah.
there are volumes on the lessons learned from Hubble and other things, and everyone knows on this program they have one shot.
Yes. So that ties into another question, which was, what did we learn from constructing Hubble that helped us in constructing Webb?
The lessons are many. First of all, one of the things that happened early, people may not remember this, but there was a problem with the Hubble in addition to the optics, where they were getting differential torques on the solar panels. And they could have been warned of that by the people doing the keyhole reconnaissance satellites, because they were basically the same size ballpark, roughly the same configuration as Hubble. But nobody was cross-cleared. The people who had the knowledge could not pass it to the Hubble people because they weren't cleared for that highly sensitive reconnaissance program. In this case, the National Reconnaissance Office coordinated with the contractors and with NASA very openly. The extent of which I don't know because I don't need to know, but we do know that they coordinated very closely. So that was one big thing. The other one is that I noticed earlier that in the earlier talk that TRW was bought, the contract was initially awarded to TRW in 2002, and they were bought by Northrop Grumman in 2003. That means, frankly, that the buying company didn't have much chance to mess things up that were already in process. Whenever there's always a temptation, I wasn't there, by the way, but I know generically there's always a temptation in mergers and acquisitions for the buying company to think they know better than the company they buy. And Northrop bought TRW so early, and Northrop had no competing organization that could think it was smarter. So they basically let the TRDW people do their job. That's why, for example, the vice president of the program today is was the vice president before 2002. So they've had very good management continuity. So they had good management continuity at a corporate level. The program had a fairly free interchange with people who had a lot of experience in the national, in the NSA, who could not talk in general in the case of Hubble. So that problem didn't happen. One of the things that happened to the Hubble was it was put on ice because of the Challenger disaster. And so the whole thing was warehoused and stopped, which meant they lost all management and technical continuity. And so they restarted it after several years because they needed the shuttle to launch it. So the whole program had a huge disruption in the case of Hubble. And then thirdly, of course, there was the fact that the testing was not done correctly. If you read the Allen report, a low-level technician made a mistake in doing the interferometric testing of the primary mirror, and no supervisor caught it. You know, which is just amazing that somebody would change a procedure in a test process of that sensitivity, and it didn't require sign off by quality assurance. It wasn't signed off by management. No engineer was standing there watching the testing being done. So and some of this happened, of course, because in the middle of the Hubble telescope, not at the end, not at the beginning, at the middle, Ealing was, I can never remember the companies. It was Ealing, I think, was bought out by PerkinElmer or vice versa. So you had competing companies merged in the middle of the whole thing. So there were a whole bunch of differences there that are lessons learned, both on a managerial, programmatic, and technical basis. And all those lessons, I'm sure, were applied. The testing was taken most to heart. I mean, anybody who's ever built a telescope, whether it was an amateur astronomer or somebody working for the National Reconnaissance Office, you'd expect to test the entire telescope assembly. And they didn't do that with Hubble. They figured the primary mirror, they figured the secondary mirror, and they launched it. They didn't put them together and perform a complete front to back test of the optics. And that was one of the things they had to spend a lot of time on this program with that huge chamber at Houston. Right. Because, you know, there's no facility you could do with that. So they had to basically pull the old one out of mothballs, make huge changes to it at great cost and time, expense. Yeah. But you had to do it.
Right.
I'm sorry for the length of that.
No, that was great. That was really interesting. So you can talk as much as you want.
Well, I need to answer some of the other questions. So
okay, the next question is: once the telescope is in orbit or at its position, how susceptible will it be to micrometeorite strikes?
As much as anybody else.
Okay.
Frankly, the only time, trying to remember, certainly the housings offer some degree of protection. It's not as highly protected as the Juno mission was that went to Jupiter into a pretty hostile radiation and micrometeors environment because of the planet Jupiter being there. It is, of course, susceptible to something happening. Frankly, I would worry much more about the launch with all the space junk. And I'm sure that launch window is deconflicted with Space Command because they track all those tens of thousands of things out there. And I'm not worried about hitting, you know, Starlink, even though astronomers find those extremely annoying when they show up in their images. I'm not talking about Starlink. I'm talking about just junk, you know, loose screws, somebody leaves, you know, a wrench falls off, which has happened, you know, in the ISS or any of several things, or the case where I believe it was the Chinese did an active interception, a kinetic interception of a satellite as a defensive test. And that produced a huge cloud of space junk. I would worry about that much more than I would worry about the environment at the L2 point.
Okay. I don't know if this is what...
Nothing in this world is certain.
Yes.
Everything is possible. Nothing is certain.
When I read that question, what I was thinking about, and I don't know if this is what Jeff was thinking when he asked it, was I look at the shield, the heat shield, and it just looks so fragile to me.
Oh, yeah.
I'm less worried about I get why it matters if things hit it as it's on its way out, but I imagine something popping through that heat shield and.
Well, it's not that highly tensioned.
Yeah.
It's not like it'll explode. It would just produce a hole.
Yeah.
It would just produce a hole. And if you had the world's worst luck and it came down perpendicular to the shield and went straight through, so you had a straight through path for heat, that's extremely unlikely.
All right, good.
So, and it would be a very small amount of area.
Right. Do you know if they considered assembling Webb in space or once it was in orbit, and why or why not for thinking about assembling parts of it up in space?
Probably because of the cost. This would be something they would have done in that very early 1994. No, 1994. No, what is it?
In the early days.
This is the problem with being alive too long. 1989 to 94 period. That was during the period of trade studies and conception. That's where they would have considered that.
Okay.
And to my knowledge, they probably at that point would have looked at the costs of doing it, of setting it up, the launch costs.
Okay. So related to that, you talked a little bit about this.
Oh, by the way, there would be another problem. You'd still have to integrate and test the thing on the ground anyways.
Okay.
You can't, once you put it up in space, there's limits to what you can do by way of modification. So if you're doing an integration, like when you're doing an integration and test program, you do it in the most benign environment you can get initially. So, and then you want to be able to get back to that environment to fix things.
Okay.
So if you are assembling it up in space, you'd still want to assemble it on the ground anyways to test it.
Got it.
So it wouldn't buy you that much. It would have and you still would want to send it when you first did the trans-orbit injection, you'd still want it folded up from reasons of momentum. You wouldn't want to have all those flaps sitting out there subjected to the G loads.
Okay. You talked a little bit about this, but again, I just want to put it as a straightforward question. What are the advantages that make it worth having Webb set out at the L2 Lagrange point so far away from Earth where we can't service it? So like pros and cons for putting it there.
Well, first of all, if it was in orbit around the Earth, you would not be able to build the shield the way you did. By having the Earth and the sun in a line, a single shield will shield you from both the thermal radiation from the back of the Earth, as well as that of the sun. So there is an advantage. In other words, even though you're exposed to them out here, because you're orbiting at 200,000 miles radius out here, so you will be exposed to the sun and the Earth all this time. The sun will not be in the shadow of the Earth. But that means a single orientation of a single alignment of the telescope to shield it from the sun also shields it from the Earth. So that's the advantage of being out here. If you were up here, I don't know if you can see there
it is.
There you can see it. If you were out here, you might shield yourself from the sun, but then you would have difficulty shielding yourself from the Earth. So by putting itself there, it also, again, it's very convenient for monitoring it. And by putting it farther away, you reduce the impact of the Earth as a radiator. Because don't forget, the sun might be bright, but the Earth absorbs all this radiation. And assuming there isn't too much CO2 in the atmosphere, all the IR comes back.
Right.
So,
okay.
Having it far away from the Earth makes sense. Remember, it's only 1 million miles from the Earth. It's 93 million miles from the sun. So there's a diminishment of the sunlight that doesn't happen with the Earth if it was closer. And if it was closer going around the Earth, you would have a nightmare of managing the heat shield, the sun shield. It would have to be a sun-Earth shield. You'd have to have 2 of them, potentially. So it's much simpler to put it out there.
Got it.
But it does make servicing at the present time virtually impossible. Now, from my perspective, since there are people who have ambitions to go to asteroids, this might be a nice intermediate test case.
So related to that, we had a question. Could they eventually service Webb with a robotic service mission? Do you think that that's a likely scenario?
Likely is a hard word to quantify.
Okay.
Because there's money involved. It comes down to will, because the technology certainly is feasible. The question is there will? John Kennedy said it very well. when he initiated the Apollo program in his speech where he said, evidence is shown, I won't get the quote quite right, but he said that the evidence is shown that it is technically feasible, provided we have the will. So that's what it would come down to.
Got it.
And like I said, it could be 5 or 10 years from now, Mr. Musk will trot forward and say, hey, I'll do it.
Mm-hmm.
So who knows?
Okay. We will see.
My concern is the next year or so. Okay.
Yeah.
Now that's everybody's going to be biting their nails for those first 100 days. They've done everything. I think they've done everything they could, but
yeah.
Okay.
Yeah, that's going to be.
It's what my friends at Wright-Patterson Air Force Base used to call an unprecedented system.
Yeah. Yeah. It's going to be an exciting year to watch everything as it goes, though.
Yeah.
Yeah. My last two questions are more in what I was calling the science realm. Do you know who will decide which proposals will be chosen for the web-based projects?
Usually these things, I can tell you how it's done usually. Usually there's a peer review panel. It goes through an initial technical screening by the people at the Space Telescope Institute, the staff, and then they send it out to peers to get reviews and then they rack and stack them and rank them. So okay. It'll be done pretty much the same way it was done with the Hubble. I'm not aware of any agreements for the Webb of proprietary interest for some of the people, some of the observers. That became a bit of a limitation on what the Webb people could do. They actually had some pictures they'd taken early through the Webb, through the Hubble, that they could not release because the principal investigators for those projects said, no, I want to just hold this data myself and do my research before you release the pictures. And they had signed proprietary rights agreements with those people. I don't think Webb's done that. I think that's another lesson they might have learned.
Got it.
Eventually, it'll all be public, of course. It'll all be probably sent down to Champaign-Urbana, like the digital Sloan Sky Survey data.
You got it. That's my alma mater. So, all right. The last question I had here is in reference to one of the other new telescopes that's being planned, the Nancy Grace Roman Telescope, which I think was announced last year, if I'm right. And what will that telescope be able to do that Webb cannot?
Don't know.
Okay.
Sorry, I honestly don't know.
That's okay. Like I said, I wasn't too sure about those two. So
yeah, sufficient unto the day is the evil thereof.
Yeah. No, that's I had missed the announcement about that as well, and so I was Googling it while we were while you were talking to see and make sure I had any sense of what was going on. But I don't want to attempt to explain the science of it after just a quick Google. Well,
I'll have to Google myself, and I won't try to explain it either until after extensive Googling and reading.
Yeah, I think the main thing was it's a smaller Hubble size mirror, and I think it's supposed to do more of a wide area and cover it so it can cover more space quickly. And it made it sound, from what I was reading, it made it sound like Webb is more focused on taking detailed information in localized places. But
yes, that shows up in that 2.2 or 9 arc minute field of view. You have to cue it by something. You have to cue it. Point it to something. You can't just, you're not going to map the whole sky survey with this. It's not like the Large Synoptic Array, which I think is now the Vera Rubin telescope. It's not like that. It's not like any of the big automated survey instruments that are in place right now. It's like the Dark Energy camera down at Cerro Torrola, which was built at Fermilab, by the way, down the road from me. It's not like that. This is you're looking through a soda straw. So it's got to be cued by other sensors. They will do some survey work, I'm sure, but it's a very narrow field of view instrument. On the other hand, if it's up there for 10 years, they'll get a lot of good results. Even 5 years, they'll get a lot of good results. I hope it's closer to the 10 years, of course.
Right. I will send that question to Dr. Cackett as well, so he's thought about it before he has his talk, so that he can also address it. So everyone has to come back now.
Several people have registered for the next.
Yeah, good.
In the course of this talk, Mark,
I'm sure it'll be a good one with Ed doing it.
I have a couple of questions that came directly to me. Do you think the JWST will have an extended lifetime like the Mars rovers have accomplished?
That's what the goal is for. There, like I said, there have been many of these vehicles, including the Voyagers, that were originally spec'd to operate for like 10 years. And, 30 years later, they're still working. The problem with the JWST, like with the Hubble, is consumables, which is the propellant. So the management of the propellant, how little they can use the reaction thrusters in the vehicle, in the spacecraft, is what's going to drive that, assuming nothing outright breaks. So the lifetime is, right now, the system is designed to run for 10 years, but the propellant or longer. But you would nominally derate that. If you're going to, John Roebling said it when he designed the George Washington Bridge. Somebody asked him how big a safety margin did he put in the George Washington Bridge, and he said 18. So when they said the requirement was for 5 years of operation, that's after deployment and commissioning. When they said the goal was the objective, the requirement was 5 years, that means they had to engineer it to last longer. And it may go beyond that if they don't run out of consumables. And that's why the mission planning is so important. And I'm sure there are people doing everything they can at the Space Telescope Institute to optimize the usage of that instrument so it captures as much data as possible with as little expenditure of propellant.
Okay, good. I've been hearing speculation, but it is all speculation. Another question, would it not be possible to place the spacecraft in the shadow of the Earth?
Well, the problem with that is it's not a stable location.
Yes.
The L2 point itself is not gravitationally stable. The slightest thing, like the solar wind against the sails, will push it off. So that's why they go, there are two types of orbits here. I didn't mention it, but there are two types of orbits that they do out here. One is called a les Ajeux orbit, which looks almost chaotic, but it's not. But it's not closed like this. And the other one is the so-called halo orbit. And both have been used by spacecraft. The halo orbit is better for repeatability and control, which is why given the solar shield and everything else they're fighting, they chose the halo orbit. If they tried to put it there fixed, they would actually consume much more propellant. They'd be constantly fighting to keep it there. Whereas here they actually have the orbital angular momentum of the halo orbit that actually which is the vector of the angular momentum. The rotation axis is out this way along the line of the Earth-Sun system, and that tends to stabilize it. So that's part of why they chose the halo orbit, is it's actually more stable than other orbits would be. This point here is actually itself unstable. A slight breeze and you'll be blown off it, and then you got to fight to get back. And if you try to stay there, you're going to use more propellant than letting the angular momentum keep you in this orbit.
Thank you very much, Mark. I really appreciate it. I think that our guests have as well. We have the next program coming up December 7th. And I did put up the shortened URL. Megan put up the complete Eventbrite URL.
Thank you. And someone also asked me about the Jerry Duniford talk. We don't have an event link for that one yet. That will be November 17th, but keep your eyes out. We will get that posted on the planetarium's social media and website fairly soon. So we'll have that as well.
And the January program will not be directly related to Webb, but it's on cosmology. And that will be back on our fourth Tuesday, which is our usual schedule. We had to change it for the December program.
Yes, much of what we're going to learn from Webb will help us with understanding cosmology. So loose link.
All right, well, thank you everyone for coming. If you do have questions, let me give you my email address again. I will be happy to answer questions and to add people to the email list or send you information about programs. That's the wrong one. It's just JDYE@DetroitPublicLibrary.org. I copied the wrong thing. Okay, thank you everyone for coming.
Thank you. Have a good evening, everyone.
And thank you for your participation, everyone.
Yes, and thank you, Mark, for a great talk.
Okay,
Yes, thank
and
you very much, Mark.
yeah, well, cross your fingers, light a candle, and whatever else it takes for a successful launch and deployment.
Yes.
Bye.
Goodbye.